This video is an overview of the liquid phase transport portion of the Flame Extinguishment Experiment 2, or FLEX2, that we are currently performing at Glenn Research Center. FLEX2 liquid phase transport tests are performed using the MDCA chamber insert assembly, which you see here being removed from the Combustion Integrated Rack, or CIR. MDCA, or the Multi-User Droplet Combustion Apparatus, is designed to support multiple droplet combustion experiments that investigate fire safety in the science of burning liquid fuels. The chamber insert assembly houses the fuel reservoirs, needles, igniters, and fiber that are used to perform a test point. It also houses the MDCA color camera, which provides real-time video of the hardware setup and combustion event. The FLEX2 liquid phase transport tests study how processes that transport mass and energy influence the combustion behavior of a bicomponent fuel droplet. These processes include mass diffusion, convection, and preferential evaporation. Mass diffusion involves the transport of mass through random molecular motion. It's the process by which molecules spread from areas of high concentration to areas of low concentration. The diffusion coefficient for a pair of fuels describes how quickly they diffuse into each other. A larger diffusion coefficient leads to a faster rate of diffusion. If given enough time, the molecules will eventually reach equilibrium. Convection is the movement of macroscopic fluid parcels. This movement, or internal flows, is driven by the differences in surface tensions of the two fuels. A greater difference between the surface tensions leads to stronger internal flows within the droplet. The effects of both mass diffusion and convection lead to mixing in the fuel droplet. At intermittent points during mixing, each fuel reaches the droplet surface. Once at the surface, the more volatile fuel tends to evaporate and form a gas layer around the droplet, changing the droplet's composition. This process, where one component of a mixture tends to evaporate first, is known as preferential evaporation. The FLEX2 liquid phase transport experiment studies different fuel mixtures at different concentrations to compare the effects of strong and weak internal flows. The propanol-glycerol fuel pair will display strong internal flows due to the large difference in their surface tensions. During combustion, these droplets may also absorb water from the surrounding environment, and the relatively high surface tension of water will add to the strong flows. The strong flows increase preferential evaporation of the more volatile fuel, in this case propanol. The heptane-hexadecane fuel pair will display weak internal flows due to close surface tensions. The weak flows decrease preferential evaporation of the more volatile fuel, in this case heptane. We're performing the propanol-glycerol test points now, and the heptane-hexadecane test points are planned for a later date. This test point video shows a fuel mixture of 95% propanol and 5% glycerol being dispensed from one of the needles. This test point takes place in 40% oxygen and 60% helium at 1 atmosphere. In high-speed video, the droplet gets bigger as fuel is dispensed. When the droplet is the correct diameter, the needles are stretched to its edges, which causes less force to be imparted during droplet deployment. The MDCA color camera zooms out for a larger field of view. Once the color camera light goes out, the needles will simultaneously snap away from the droplet, leaving it free-floating. After a short delay, the hot wire igniters ignite the droplet. Due to hot soot particles, the flame glows bright yellow. Some of these particles penetrate the flame. The bluish glow is a thin spherical layer of gas surrounding the droplet and the soot particles. A sudden buildup of glycerol at the droplet surface causes flame contraction, which occurs here just prior to flame extinction. The remaining droplet is mostly glycerol. Slow-motion video of the end of the burn shows flame contraction. Compared to the previous test, this test has a slightly smaller fuel droplet and the chamber environment is at 3 atmospheres instead of 1. Due to the higher pressure, more soot is formed, making the flame brighter. The higher pressure also increases the radiant heat transfer from the flame and the droplet burning rate and temperature. The hotter droplet leads to stronger internal flows and faster diffusion. From the image data, we measure the initial droplet diameter and the droplet diameter at flame contraction to determine the diffusion coefficient. This data helps us to better understand the fundamental dynamics of combustion in space and of practical fuels that have multiple components, such as gasoline and jet fuels. Understanding how multi-component fuels burn in microgravity will lead to improved fire safety in space vehicles, as well as liquid fuel engines that are more efficient and create less pollution. We hope this video helps to explain the science of CIR MDCA FLEX2 liquid phase transport. We truly appreciate all your hard work that keeps us doing science on station. We couldn't do it without you.